Alrighty, so we just sized a spacecraft for stiffness. Now we're going to do the same thing for strength. So let me draw another one. There's a satellite. And this one has L equals 1.8 meters, diameter 0.4 meters, thickness all in meters, of course. Young's modulus 71 gigapascals, density 2800 kilograms per cubic meter. Okay, now as you're on your rocket ship, well, I guess I realized in the last video that maybe rocket ship isn't the most professional of engineering terms, so we're going to say launch vehicle now. As you're on your launch vehicle, you may have some maximum loads, and your loads are going to be, let's say, in the Z direction and the Y direction. So you have FZ, FY, and these loads are measured in terms of acceleration. So we have, say, we know from some reference for the launch vehicle that our maximum load in this direction is going to be 3 times the acceleration of gravity, and let's say that the maximum acceleration in any lateral direction will be 1.3, and this is combining the possible static and dynamic loads together. Alright, and then the last thing that we are going to have to take into account to find out what the maximum stress should be that this can withstand is going to be the just a what's called I think it's called a load safety factor, and what this is just going to be some value like 1.1 that you'll be given, and that's a safety factor for any miscalculation in these here accelerations. So what we can do to figure out what the maximum stress needs to be is going to be use just typical superposition stress. We know that this is going to bend, and we know that this one's going to put it in tension, compression, whatever, and we of course know our bending moment equation. C is distance to the neutral axis, and I is moment of inertia, of course. We know what the cross-sectional moment of inertia for a thin-walled cylinder is. And then for the tension stress, that's going to be simply force divided by area. Area, of course, being 2 pi RT. Alright, and then last thing that you might want to add here at this point is that so your design load is going to be your calculated load. Fy or Fz times design load factor. So in order to calculate the, say, let's call it our design stress, what we need to do is we need to take this factor and apply it to here. We're also going to have to make some substitutions in order to make this equation something that we can substitute everything into. So let's do that now. So 1.1, what's the force going to be? Well, it's going to be mass times 1.3 times the acceleration of gravity, and L here is the length of the satellite, so 1.7, and distance to the neutral axis, if you were to just make cross-section symmetrical, yeah, the highest bending stress is going to be, of course, right here. So that distance is the R. Okay, moment of inertia, already did that. Finally, same thing we just did. Design load factor, mass times 5 G's. Okay, area. Plug all that into your calculator, and you're going to get the maximum design stress considering this load factor, this design load factor that your spaceship should be able to handle in order to go on the launch vehicle. And that's going to be, once you plug in all your factors, 244 megapascals. There you go.